Okay, first lecture in a while. Um, since the last one, I'm now required to do everything from home, so that's what I'm doing now. And since I don't have a chalkboard or a whiteboard, what I'll be doing is using this software where I can render um, mathematical equations as I type. So we have just one chapter left. It's chapter 7. I'll make a quick note here. So this is chapter 7 in the textbook or ebook from WebAssign, chapter 4 in my notes that are on the resources page of the course website. We're just going to cover sections 7.1, 2, and 3, which is not what I planned, but it's actually consistent with what I've covered in the past when teaching this class. And this deals with the entirety of chapter 4 in my notes that corresponds to that. So we're going to see very different techniques for solving linear differential equations with constant coefficients. And that is it's known as the integral transform. There are several of those. This particular one is called the Laplace transform. So I'm going to show you what it is, give some examples and some formulas stemming from it, and then I'll briefly talk about why it's useful to us for solving differential equations, which we'll actually get into next class. So, um, so, so we're given some function f of t, the Laplace transform of f of t, and it's denoted usually, different books use different notation, but what's commonly used is um, some sort of fancy L for Laplace of f of t. And the function that we're given is a function of t. The output of a Laplace transform is also a function, but a function of a new variable, which I'll call s. So it maps one function to another. And what is that function? It's defined as an integral from 0 to infinity, of e to the minus st f of t dt. So the idea is you evaluate this integral with respect to t, but you have this parameter s. So as far as evaluating the integral is concerned, s is treated as a constant, but the result that you get will depend on s. It'll be a function of s. Um, so for whatever function you want to take a Laplace transform of, you can plug it in here, work out this integral, get your result in terms of s. That is your um, Laplace transform. Okay, so function of s. So I'm going to show a couple examples. So let's let the f of t be equal to 1. Then what we have is Laplace transform of f of t will be equal to the integral from 0 to infinity of e to the minus st times 1 dt. So now we're just going to integrate e to the minus st from 0 to infinity. So that's going to be minus e to the minus st over s, just from working out the integral with respect to t. And remember, when you integrate an exponential function, there's a constant times your variable, you must divide by that constant. In this case, the constant is minus s. And we have limits. This is a definite integral. Okay. So we have a vertical bar here indicates that these are the limits that we plug in. Now, the thing is, we work with the uh, everything being positive here, both t and s. So what we have here is a negative exponent. So if we let t go to infinity, this exponential is going to go to 0. Um, so we'll get 0 from plugging in the um, upper limit. And if we plug in 0 for the lower limit, all right, so that's what we get there, but e to the 0 is 1. So then the minus and minuses cancel out, that's giving us a plus. So our final result is 1 over s. Okay, so we're considering uh, functions defined on the positive real axis, f of t for t positive. Um, and we get a Laplace transform as a function of s, where s is also taken to be positive. So the Laplace transform of 1 is 1 over s. All right. Let's do another. Let f of t be equal to sine t. So what happens in this case is I'll need to make this a multi-line formula. Okay. So f of s, which is Laplace transform of f of t. So that'll be the integral 0 to infinity e to minus st sine t dt. Now, this integral would require integration by parts, which is actually be pretty nasty because if you were to work this out in full, you would carry out integration by parts twice and wind up with something, it'd be the same integral you started with, e to the minus st sine t, times a constant. And you move it to the other side and divide and so forth. I'm not going to go through all that. It's really not necessary. But what I'll show is the final result of um, integration by parts. So we have 1 over 1 plus s squared, and we have so integration parts will give you minus e minus st cosine t minus s e to the minus st sine t with limits 0 and infinity. So what happens when you plug in the limits, again, when you plug in t equal infinity, or let t go to infinity, then everything here would go to 0. So then you would subtract from this the result from plugging in t equals 0. Well, this part would be 0 because sine 0 is 0. Cosine of 0 is 1. And the exponential would be 1 when t is equal to 0. So what's left is just going to be 1 over 1 plus s squared. So that's the Laplace transform of sine. I'll do one more. E to the at, where a is assumed to be a constant. So what happens here is this is integral 0 to infinity e to the minus st e to the at and you can combine those into one exponential e to the minus s minus a t dt. So then it's the same form as this integral. It's just that in place of s, which is a constant as far as the integral is concerned, you have s minus a. So really what happens is I could work through this whole thing, but just replace s by s minus a, and it would work out exactly the same way. So what we have is 1 over s minus a. So those are a few essential Laplace transforms. And in this case, I've used the definition, but we are actually not going to be making use of a definition at all for the rest of the way. So I'm not going to give you any problems where you must use the definition directly to come up with a Laplace transform of a function. Instead, you're going to be using certain formulas that have already been worked out. So what you can find very easily, like by looking online, for instance, or in the textbook, is a Laplace transform table. And I would recommend having a Laplace transform table handy um, in whenever you're working on problems, and also when you're taking the final exam, you should um, have one available. Um, so there are many functions for which Laplace transforms have been worked out. All I'm going to do is just show you a few, and this corresponds to theorem 711 in the textbook that you would see on WebAssign, and this is relevant for the homework on section 711. I'm not going to give you the full theorem, just ones that are actually needed for the homework. So what we have is okay. I have this in my notes, but I want to have it in this um, document too. Okay, so what I have is, and by the way, these notes that I'm typing out here, even if it corresponds to what's already posted online in notes, I'm going to post these notes on the lectures page along with a link to the video. So what we have is Laplace transform of t to the n. So we've seen the case where n equals 0, but for a power of t, in general, what you get is n factorial over s n plus 1. So we saw that when n equals 0, we get 0 factorial, which is 1, over s to the first power. Laplace transform of t would be 1 over s squared. Laplace transform of t squared would be 2 over s cubed, and so forth. So whatever power you have here, you always have one greater than that in the denominator, and then you have its constant up top. All right, so that's the powers of t. Actually, I'm going to move this onto a new page. Now, we also have, just for to make things self-contained, the exponential that I just showed you. So that's 1 over s minus a. All right. And then we saw sine t. So more generally, sine of kt, where k is a constant. So that's going to be k over s squared plus k squared. And similarly, if you have a cosine of kt, then that would be s over s squared plus k squared. So notice the ones for sine and cosine are quite similar, just they have a different numerator. So the constant for sine and then s for cosine. All right, so these transforms will be enough to get you through the homework for 7.1. But we'll see some other transforms as we go through the rest of the chapter. Now, other formulas that will be needed. The Laplace transform is linear because it's defined in terms of an integral. The definite integral is linear. So what do I mean by that exactly? I have the following relationships that Laplace transform of a sum is just equal to the sum of the transforms. So in some cases in the homework, you'll have a function to transform that is a sum or difference of several terms. So you can just transform the terms individually and add the results together. So that part works out nicely. Similarly, if I'm taking Laplace transform of some constant times a function, f of t, then I can go ahead and transform f of t, or look up its transform, and then just multiply it by that constant. That's what's meant by a linear operation. Just as the integral of a sum is the sum of the integrals, or constant factors for integrals, you can pull them out, things like that. So as an example, the Laplace transform of 1 plus t is equal to the Laplace transform of 1, which is 1 over s, plus the Laplace transform of t, which is 1 over s squared. Okay, so let's break it down to each term individually. Other formulas that you will need for the homework for section 7.1, trig identities. Okay. And there's just a few. These are ones that are good to know anyway. So we have the cosine of a sum or difference. Actually, I believe it's a difference is what's included, but you can adapt it for sum. Just replace b with minus b. So that's cosine a, cosine b, plus sine a, sine b. Or another way of putting it, if I had plus or minus, then what you have here is minus plus. So whatever sign you have in here, it must be the opposite sign here. So that's one trig identity. A very good one to know, just in general. Cosine squared of theta. You use a half angle formula, so 1 minus cosine of 2 theta. Sorry, that's 1 plus all over 2. Whereas sine squared theta, it's 1 minus cosine 2 theta all over 2. And one more. That sine, this is called a double angle formula. Sine of 2 theta is equal to 2 sine theta cosine theta. So what's convenient is, because really one of the homework problems, you're given an expression that's like the right side, and we haven't learned yet how to transform a product of functions. We know how to handle a sum, but a product is not so easy. But what you can do in this case is you can transform, use trig identity to rewrite a product of a sine and cosine of the same angle as a sine of twice that angle. And this is something that you can work out the transform of using the formulas up above. So these trig identities will help you rewrite the given function into a form for which you can use the formulas above for known Laplace transforms. Okay, so the last thing I want to take a little time on is how is the Laplace transform helpful for solving differential equations? So there's a few reasons I can give. The first is that Laplace transform transforms a differential equation into an algebraic equation, something that would be much easier to solve. So the idea is we'll learn how to take the Laplace transform of a differential equation using techniques for Laplace transforms of known functions and also derivatives. And then what you get is an equation you can solve just by algebraic manipulations. That will give you not the solution, but the Laplace transform of a solution, and then you go backwards, use what's called an inverse Laplace transform. Basically, you're applying these formulas in reverse. You have an expression like this, and you want to go back to a function of s. You want to go back to a function of t. So we'll learn all about that next time. Um, but you get a simpler equation um, from the transform. Second reason is it's easier to take initial conditions into account. You're accustomed to um, having constants C1 and C2, and you need to do a whole lot of algebra to find C1 and C2. In this case, the initial values are worked into the transform of the equation. So after that, they're all accounted for. You can forget about them. So it's a less cumbersome process that way. Also, less cumbersome for another aspect, that is solving inhomogeneous equations. Right now, the techniques are undetermined coefficients and variation of parameters. So if you have an inhomogeneous equation, you have something non-zero on the right side, you're just going to take the Laplace transform of that function too. And then it's already taken into account for the purpose of finding the transform of your solution. And so no need to solve for a whole bunch of unknown parameters, for instance, or work out nasty integrals most of the time. And one more reason is be used to work with differential equations continuities. So if a coefficient or what we'll see is the right-hand side, if that has a piecewise definition, if it has discontinuities in it, the Laplace transform makes it remarkably easy to take those into account, because Laplace transforms have been worked out for these kind of functions also. And because we haven't dealt with that at all, the techniques that we have aren't really helpful for uh, right-hand side functions that have discontinuities. But here it's, I wouldn't call it easy, but at least it's doable, which is more than what we had. So this is why we will be using Laplace transform as another technique for solving differential equations. So starting next class, I'll actually show you a process of how that's done. So until then, you have a homework for 7.1 that's due on Monday the 20th. If you have any difficulties with that, certainly let me know.